Welcome to G Fun Facts Online. Today, we are descending into a realm of eternal darkness and crushing pressure. The ocean floor has long been considered the final frontier for human exploration, a place of mystery and alien landscapes. Yet, in our frantic race to avert a global climate catastrophe, this abyss is poised to become something far more pragmatic and essential. It is set to become humanity's most vital vault. As atmospheric carbon dioxide concentrations breach historic thresholds, the solution to our warming planet may not lie in the skies above, but deep within the geology of the seabed below. This is the story of how we plan to bury the sky. Let us begin with the obvious question: why go subsea? For decades, the concept of carbon capture and storage, or CCS, has been technically feasible. We know how to scrub carbon from industrial smokestacks. The problem has always been where to put it. Onshore storage, burying it under the land we live on, often faces fierce public opposition. It is the classic "not in my backyard" or NIMBY phenomenon. People are understandably nervous about living on top of a gigaton of compressed gas. Furthermore, land is a finite resource, and storage sites compete with agriculture, housing, and wilderness. Subsea storage flips this dynamic entirely. By leveraging the vast, unpopulated expanses of the continental shelves, we can access geological formations of immense capacity, far removed from human settlements. But the allure of the deep is not merely about avoiding angry neighbors. It is fundamentally about geology and physics. The offshore environment offers two distinct advantages: scale and safety. The world's continental shelves are thick with sedimentary basins. These are the exact same formations that trapped oil and gas for millions of years. Now, we are looking to repurpose them to imprison the carbon released by burning those very fuels. Beyond the rock itself, the ocean offers a unique safety feature. The sheer weight of the ocean provides what engineers call a hydrostatic head. This is an immense column of water pressure that acts as a secondary seal. It ensures that even in the unlikely event that CO2 were to escape the rock, it would face significant physical barriers preventing it from ever reaching the atmosphere. To understand how we actually do this, we need to look at the geology. We must understand the storage complex. A common misconception is that we are pumping gas into a hollow cave, like filling a giant underground balloon. That is not how it works. We are injecting carbon into microscopic pore spaces within solid rock. Think of it less like a tank and more like soaking water into a rigid stone sponge. The ideal storage medium is highly porous and permeable sedimentary rock, typically sandstone found 800 to 3,000 meters below the seabed. There are two main types of containers we look for. The first are depleted oil and gas fields. These are the low-hanging fruit of the industry. We know they can hold fluids because they successfully held hydrocarbons for eons without leaking. The infrastructure, such as platforms and pipelines, often already exists, though it usually needs retrofitting to handle the corrosive nature of pure CO2. The second and much larger option are saline aquifers. These are vast underground lakes of unusable saltwater. Unlike oil fields, they are not confined to narrow geological traps, but extend for hundreds of kilometers. Here, the CO2 is injected into the brine, where it begins a complex geochemical dance. But a good reservoir is useless without a lid. Above this porous sandstone must lie a caprock. This is a dense, impermeable layer of shale, clay, or salt. This is the lid of the jar. Without a verified continuous caprock, injection cannot proceed. In the North Sea, for instance, kilometers-thick layers of plastic clays seal the reservoirs, having successfully trapped natural gas since the Jurassic period. Now, let's get into the physics of what happens once the carbon is down there. This is where the science gets truly fascinating. Once injected, CO2 does not just sit there idly. It undergoes a metamorphosis driven by four distinct trapping mechanisms, that actually increase security over time. The first phase is structural trapping, which happens immediately. When CO2 is injected, it is in a supercritical state. This means it is dense like a liquid, but viscous like a gas. However, it is still lighter than the saline water around it, so it floats upward. Structural trapping occurs when this buoyant plume hits the impermeable caprock and physically pools there, unable to rise further. Over the course of decades, we enter the second phase, residual trapping. As the CO2 plume migrates through the microscopic pores of the rock, it pushes the brine aside. But when the injection stops and the tail of the plume passes, capillary forces snap off tiny droplets of CO2, trapping them in the pore throats of the rock. The CO2 becomes stuck, exactly like water remains in a sponge even after you squeeze it. It is physically immobilized in the microscopic architecture of the stone. As we move into the scale of centuries, we see solubility trapping. Over time, the interface between the CO2 gas and the brine allows the gas to dissolve into the water, creating carbonic acid, essentially sparkling water. This is a crucial turning point because CO2-saturated water is slightly denser than the surrounding brine. This causes it to sink, creating a convection current that churns the reservoir and accelerates further dissolution. Once dissolved, the CO2 can no longer float to the surface. It is gravitationally secure. Finally, over millennia, we reach the ultimate phase, mineral trapping. The carbonic acid reacts with the minerals in the host rock, such as calcium or magnesium silicates, to precipitate solid carbonate minerals. The CO2 literally turns into stone, becoming calcite or magnesite. It permanently fuses with the geology of the Earth, locked away forever. Creating this geological vault requires a symphony of extreme engineering. We are talking about operating at pressures of over 200 bars and temperatures near freezing. The transport network itself is a massive challenge. For short distances, high-pressure pipelines are efficient, but they must be designed to resist running ductile fracture. This is a catastrophic zipper-like burst caused by the rapid decompression of CO2. For longer distances or smaller volumes, the ship-to-shore model is gaining dominance. We are seeing the rise of specialized carriers, similar to LPG tankers, but kept at roughly 15 to 19 bars of pressure and minus 26 degrees Celsius, transporting liquid CO2 to offshore receiving terminals. On the seabed, the infrastructure resembles a standard oil extraction site, but running in reverse. It centers on the subsea tree, a massive assembly of valves sitting on the wellhead. Unlike production trees designed to let pressure out, injection trees must withstand the thermal shock of cold liquid CO2 entering a hot reservoir. The wellbore itself is lined with specialized cement and steel casings resistant to carbonic acid corrosion. These are smart wells, equipped with fiber optic sensors known as distributed acoustic sensing, to listen for leaks or rock fracturing in real time. The world is finally waking up to this potential. The North Sea is currently acting as the Silicon Valley of offshore CCS. The undisputed leader is Norway with its Northern Lights project. Building on 25 years of data from the Sleipner field, where they have injected 1 million tons of CO2 annually since 1996, Northern Lights is the world's first open-source CO2 transport and storage network. It accepts carbon shipped from across Europe to be buried 600 meters below the seabed. The Netherlands is also moving fast with projects like Porthos and Aramis, utilizing depleted gas fields to store emissions from the port of Rotterdam. In the Asia-Pacific region, we see a sleeping giant awakening. Malaysia and Indonesia are exploring CCS hubs to decarbonize their gas exports. Japan, which lacks domestic storage capacity, is pioneering the concept of transboundary CCS, planning to ship its emissions to storage sites in Southeast Asia and Australia. Meanwhile, in the United States, the Gulf of Mexico holds storage potential in the hundreds of gigatons, thanks to a vast existing pipeline network and porous geology. However, No technological intervention is without risk, and there are uncalculated variables we must discuss. Critics point to the induced seismicity. Injecting fluids raises pressure underground. If this pressure lubricates an existing fault line, it can trigger earthquakes. Careful site selection and pressure management are critical to avoiding the fate of projects that have been halted by induced tremors. Perhaps the greatest risk is not the geology but the human legacy. We call these leakage pathways. The North Sea is punctured by thousands of old oil wells, many abandoned decades ago, with standards far lower than today's. These zombie wells could act as chimneys for injected CO2 to escape back to the surface. There is also the brine displacement problem. You cannot fill a cup that is already full. Injecting CO2 pushes existing brine out. If not managed, this hypersaline water could migrate into freshwater aquifers or impact the seabed environment. Legally, this entire industry relies on a delicate architectural change. Dumping waste at sea was banned by the London Convention. However, a landmark amendment to the London Protocol, specifically Article 6, created an exemption for CO2 streams intended for sequestration. This legal tweak essentially legalized the industry. Furthermore, a 2019 resolution allowed for the provisional application of cross-border CO2 transport. This enables landlocked nations like Switzerland to export their carbon to nations with storage assets like Norway, effectively creating a global currency of carbon storage. In conclusion, burying the sky is not a panacea. It does not excuse the continued reckless burning of fossil fuels. However, the International Energy Agency and the IPCC agreed that there is no realistic path to net zero without CCS. Hard-to-abate sectors like cement, steel, and chemical production simply have few other options. By turning the seabed into a vault, we are closing the loop on the Industrial Revolution. We are returning the carbon we excavated from the Earth back to the geologic deep, buying humanity the most precious resource of all, which is time. The geology is ready. The question remains whether our engineering and political will can match the scale of the crisis. Thank you for listening to Fun Facts Online.